Well, good morning there, physics students. Happy Friday to you. It is Friday, May 15th. This, for the seniors, is your last Friday of class. Oh my gosh. Wow. Well, here's what we're doing. We're going to start a new chapter here today. And I think we'll be able to get through most of the chapter. Possibly not the labs that we would normally done, and I don't know if you noticed, but we didn't do a lab in the last chapter because I just wasn't sure how to make that work very well. But we'll see. We'll at least get through some basic concepts. Here's our learning targets for today. I can define centripetal acceleration and perform related calculations. I can define centripetal force and perform related calculations. And really those two definitions are closely related to each other, I think you can tell. And the calculations are really just going to be kind of a variation on stuff that we've done before. So this is not anything really new and big. All right, the chapter that we're starting, chapter 7, is titled Circular Motion and Gravitation. And it always seems to me to be a little bit of a weird mix, but gravity makes things travel in curved paths, and especially if you're in orbit, it's nearly a circular path. So there is some relationship. All right, so we've got a circle, and I got a little guy on the circle. We could imagine this is maybe a merry-go-round. And so where this guy is sitting, if this merry-go-round is spinning, he's moving that way. Now, if we go and move this some, you see that the direction of his motion is always changing. So he's moving, he's got a velocity, the direction of the velocity is changing. Now, velocity is a vector quantity. So really, the velocity is changing. His speed might not be changing, but his velocity is changing because the direction is always changing. Saddens me a little bit that I've got this dual diagram here, and as I spin it, it doesn't quite line up right, and it's because when I attach the little drawing of the guy, it somehow shifts the balance in the computer's mind of what my picture looks like. But we get the idea. So you see that the direction is changing until when we get all the way back around, back where we started from. Oh, okay. So if the velocity is changing because the direction is changing, we had another definition way back when. It says acceleration is the rate of change in velocity. So if his velocity is changing, he's accelerating. And you say, well, what's the difference between this velocity and this velocity? Well, the magnitude is the same. It's just a difference in direction. What is the acceleration involved? And the actual, I think mathematical nuances of this get a little bit tricky to understand. I think it's a little bit easier, and so I'm going to take this, from the standpoint of, I'm going to take this in a little bit different order than how your book would do it. I want to think about what causes a change in velocity. There's got to be a force. If there were no force on this guy, you would keep just moving that way. Now let's think about applying a force to it. If we just applied a force to him that way, well, you just move faster that way. And if we applied a force this way, he would slow down. But he's changing direction. And in order to change the direction of something, we got to push kind of a sideways force. So there's a force here. And over here, in order to change direction, there's force here. And if we draw this in and say, all right, when he's up here, the force is this way. When he's over here, the force is this way. When he's over here, the force is this way. The force is this way. Oops. What do you notice about all those forces? Well, they're all pointing to the same spot. They're all pointing towards the center. The word that means towards the center, it's an adjective, centripetal. Okay? Literally, that word, towards the center. All right, so the force that's pushing towards the center is a centripetal force. A force, an unbalanced force on an object, causes an acceleration. So the acceleration caused by the centripetal force is our centripetal acceleration. Let's look at this next page. So I put two people on here. So imagine it's a big merry-go-round. And this person is a little bit closer to the center. So if we look at this as it turns, right, as we go all the way around, we know that this person made a smaller circle, so they traveled less distance, but it took them the same amount of time to go around, right? So if you go less distance in the same time, distance per time is a velocity, and if they have the same time, but one has less distance, oh, this guy's got a smaller velocity than this one, okay? The further, if we had another guy, sitting in here, you'd have a smaller velocity yet. And if we had somebody that was sitting right at the center, they have no velocity. At least no tangential velocity. This will be rotating. That's a different kind of motion. All right. So, all right, let's go on to this next page. I have some equations for centripetal acceleration. So centripetal acceleration, the value of centripetal acceleration, we go A sub c. So it's an acceleration referring to centripetal. We take v squared over r. Okay, v is our tangential velocity. Okay? All right, if I draw a circle and we're moving this way, that velocity is tangential. Okay? So a tangent intersects a circle at one point. If our motion is this way, okay, so this is tangential, and motion this way, or this direction, is referred to as radial. Okay? So we take whatever our tangential velocity is, and we divide it by the radius. Look at labels. If this is meters per second, and we got another meters per second because that's squared, and we're dividing by meters, meters cross off, and look, we got meters per second squared. And we know from the past that that's an acceleration label. So this is our real basic little formula for calculating a centripetal acceleration. Centripetal force. Okay, I'm going to start out with this. Force equals mass times acceleration. That should be extremely familiar to you. That is Newton's second law. Force, net force acting on mass, causes an acceleration. So in this case, if we're talking about forces directed towards the center, a centripetal force is going to be the mass times the centripetal acceleration. But on the last page, we just wrote that the centripetal acceleration is v squared over r, so we could say that centripetal force is mass v squared all over r. This is just application of Newton's second law, but giving it a little twist because we're talking about something that's going around a circle. Let's practice it a little bit. This is problem number 1 from page 226 in your textbook. It says, a rope attaches a tire to an overhanging tree limb. Here, I'm going to draw my tree limb, and here's my rope and tire. A girl swinging on a tire. Okay, so it's got long hair. A girl swinging on a tire has a centripetal acceleration of 3.0 meters per second. Okay, so we know that the centripetal acceleration is directed towards the center. So we got to think about our path. So the tire swings along this curve and the center is there. So our centripetal acceleration is directed that way, 3.0 meters per second squared. The length of the rope is 2.1 meters. Now, this is where we have to interpret the problem a little bit. I think they're saying, I would interpret it as the length from the center to the center mass is 2.1 meters. Otherwise, we don't have enough information to solve this problem. Okay, so if you are going to nitpick it and say, well, the rope's attached up here and she's swinging down here, yeah, then you don't have enough information to do the problem, and that's not, I'm going to say it flat out, that's not what you get to write for an answer. Okay, we're going to interpret the problem. They intended us to use that distance. All right, so that's a length, but you see that length happens to be the radius of that circle. If we gave her a good push and she swung all the way around, she'd be traveling in a circle with a radius of 2.1 meters. What's the girl's tangential speed? Well, the math that we're looking at right now says centripetal acceleration is v squared over r. We were given the centripetal acceleration and r, so we just have to solve for v squared. I'm going to multiply both sides by r, so centripetal acceleration r equals v squared. V is going to equal the square root of centripetal acceleration times r, square root of 3.0 meters per second squared times 2.1 meters. Now look at labels. Under the radical, we got meters times meters is meters squared per second squared. When we bring that out from the radical, we're going to have meters per second. That's good. Grab a calculator. Square root of 3 times 2.1, close parenthesis, equals, I've got, we only get 2 sig figs, so this looks to me like 2.5 meters per second. Pretty straightforward problem. All right, this is problem number 2 from page 228. And it says a bicyclist is riding at a tangential speed of 13.2 meters per second around a circular track. All right, there's our bicyclist. Okay. Tangential speed. So tangential speed is going tangent to the circle at 13.2 meters per second. And it says the magnitude of the centripetal acceleration, centripetal force is 377 meters. So centripetal is towards the center. So I have a force towards the center of 377 newtons. The combined mass of the bicycle and rider is 86.5 kilograms. What's the track's radius? Well, we had our formulas. Centripetal acceleration is v squared over r, and we had centripetal force is m v squared over r, right? Mass times centripetal acceleration. So when I look at that, I know the force, I know the mass, I know the velocity, I'm just looking for r. So I'm going to rearrange that equation. And the first thing I want to do is get r out of the denominator. You never leave the thing that you're looking for in the denominator. So I'm going to multiply both sides by r. So r times centripetal force equals mv squared. And now I'm going to divide both sides by FC. And so I'm going to get r equals mv squared over centripetal force. And now I'm going to plug in numbers. I was going to put a radical, and there is no radical. M, 86.5 kilograms. The velocity is 13.2 meters per second. Squared, so I'm going to put it in here twice. And we got to divide by the centripetal force. I've got room for it right there. 377 newtons. Now, remember the definition of a newton? I hope so. It's a kilogram times a meter per second squared. So, if I've got kilogram times meter per second squared, this is going to cross off this, and this, and this, and this, and it's going to leave us with meters. Woo! Meters. That's a radius. So we grab a calculator. 86.5 times 13.2 times 13.2 divided by 377 equals, looks like we get 3 sig figs this time. I got 39.978. So that's going to round up. The 9 rounds up to 10. So I got 40.0 meters. Okay, let's look at one more. So we got a 25.0 kilogram child moves at the speed of 1.93 meters per second when sitting 12.5 meters from the center of a merry-go-round. Calculate the centripetal acceleration and the centripetal force. Okay, so I got a merry-go-round. I'm going to give you a top view. So our child is sitting out here, and they are, it's a big merry-go-round, 12.5 meters from the center. And they have a velocity of 1.93 meters per second. Okay? So let's find centripetal acceleration. It's just v squared over r. So 1.93 meters per second times 1.93 meters per second. And on the bottom I got 12.5 meters. So one of the meters crosses off. All right, 1.93 times 1.93 divided by 12.5 equals, centripetal acceleration is 0. I get 3 sig figs, 298. Okay, we're not done. It also says find the centripetal force. Well, because I've already found the centripetal acceleration, I can just say centripetal force equals mass times centripetal acceleration. I could have put the v squared over r in here, but it's just doing that math again. The only reason I might do that is because then I'm not taking this rounded value in between. As long as I can see your work, I'm okay either way. So our mass was 25 kilograms, 25.0 times 0.298 meters per second squared. hey, a kilogram times a meter per second squared is a Newton. So, you know what? I still have in my calculator the math from the last one. Now I rounded off to 0.298, but I'm going to leave what was in my calculator from the last one and multiply by 25, and I get to 3 sig figs 7.45 newtons. 2 answers. All right. So, not a big stretch on what we've done before. So if we are familiar with what we've done before, should be able to add this in quite easily. We're going to have a couple practice problems as always, and I'll see you again on Monday. As always, if you have any concerns, any questions, let me know. I can help.